Hello everyone, welcome back to my organic chemistry mini lecture. Today the topic will be chirality and handedness. First, look at your first hand and then your right hand. What's the relationship of them? So you maybe say they are the same. Actually, they are not the same because you can actually cannot overlap with them. If they can penetrate with each other, you can try to overlap, but actually you cannot because they are not the same. So, and they are just a mirror image, and we call them non-superimposable if they are different. And this kind of object called a chiral. And chiral, the names come from Greek. In Greek, it means handedness. Apparently, borrow the idea of your both hand. And look at other object like this bell. This bell, the mirror image is shown here, and they are same. They are exactly same. So you can overlap them, no problem. And they are called superimposable. So this kind of object called achiral. Okay. So in organic chemistry, this is very, very common phenomenon, the chirality. Okay. Look at this 2-chlorobutane. And we can find this carbon is asymmetric center because it has 4 different group: chloro, hydrogen, methyl, and ethyl group. Okay, so this is the asymmetric center. Now this chloro group can point to you, can be away from you. So you can write 2 different isomer here. And what's the relationship of them? First, they are not same, so they are not identical. Now, if you rotate this isomer 180 degree, you'll draw it's the same molecule but in different way. Now the chloro is pointed to you because you rotate 180. Now compared with the first stereoisomer, you may notice they are mirror image now. Okay, so this is a chiral molecule. That's a chiral, and since they are mirror image, they are called enantiomers. Okay, so this is a pair of enantiomers. Usually, a molecule with one asymmetric center, like this example, is chiral. A molecule without asymmetric center is achiral, usually. There are some exceptions here. So in some special case, for example, if the structure is a spiral or with 2 plane, then they could have some substitution or derivatives be chiral. Okay, those chiral compound, they don't have asymmetric center, but that's a very special case. So in this mini lecture, I will not talk about too much about that. We will talk about the common normal case. Okay, let's look at the more example of the enantiomers. This pair of enantiomers, they have one asymmetric center. This is the cyclic alkene with the floral substitution here. Okay, this is the asymmetric center as this asymmetric center. So that's a pair of enantiomer. Another example, this is the alkyl chloride, and this is asymmetric center. That's the mirror image. They are enantiomers. This is the epoxide with the substitution here. So that's asymmetric center, and this is the enantiomer, a pair of enantiomer shown here. Last example is the bromide, and this is also a symmetric center. So this mirror image is the enantiomer. So this is a pair of enantiomers. If the ratio of the enantiomer mixture is 1:1, then the mixture is called a racemic mixture. Okay. That's a pair of famous enantiomers. It's called a thalidomide. This is a very famous incident in history. So this is called the thalidomide tragedy, because this was commercialized as a medicine for morning sick of a pregnant woman in 1950s and 60s. But this caused big trouble to the baby, and that's why it was stopped or discontinued quickly after people find the birth defect. And turns out this is a pair of enantiomers, and this is R enantiomer, and this is S enantiomer. That's the absolute configuration of this asymmetric center. And the S enantiomer is the toxic one. Okay, so this is a disaster actually in the history. When scientists found this is the toxic, they actually tried to get rid of this from the mixture. They try to just isolate the pure R enantiomer. Turns out that this, even you have 100% pure R enantiomer, it slowly converted to S. So still cannot be used as medicine. Okay, so that is the enantiomers. Just some examples. Now let's talk about what about you have more than one asymmetric center, such as this the 3-bromo-2-chloro-pentane, and since they could have different orientation, we can draw these two asymmetric center as in this molecule. So if you draw the different isomer, you can draw both chloro, bromo point to you, or you can draw chloro away from you. You can draw the both away from you. You can draw the chloro face to you, pointed to you, and the bromo away from you. So you basically can draw 4 different stereoisomers. Now, what's the relationship? If you rotate this isomer, you can have this structure, which is now mirror image with this first isomer. So apparently they are enantiomers. And then if you rotate this one 180 degree, and you can find this structure now is mirror image with this isomer. So they are also enantiomers. Now what about these two? They are not enantiomers and they are not identical. So they are called diastereomers. Same thing, these two diastereomers. And what about these two? The relationship and these two, they are all diastereomers. Usually, the maximum number of stereoisomers is 2 to the power of n. N is the number of asymmetric centers. For this example, we have 2 asymmetric centers, so square of 2 is 4, so you could have 4 different maximum stereoisomers. And if you have 3 asymmetric centers, you could have cube of 2, that's 8 stereoisomers possible. Okay. Another example of the diastereomers, this is the Fisher projection. Okay, so just remember this, although it looks like 2D, but actually the horizontal bond are pointed to you and the vertical bond are away from you. So this is an alcohol here. And so you can draw the first one, second one, third, and fourth. You can draw up to 4 stereoisomers. And these two are mirror image, that's enantiomers. And these two are mirror image, so they are enantiomers. Now what about this with this one? That's diastereomers. Same thing. These two are diastereomers. And these two diastereomers, and these two are also diastereomers. Okay. And now look at another example. This is amine, and you can draw another stereoisomer, another one, another one. See, and now mirror image. So these two are enantiomers. These two are enantiomers. And again, that's diastereomers. That's diastereomers, and that's diastereomers, and then diastereomers. Okay. More example here. That's another Fisher projection. Now this time we have dichloride. You will see it's a little bit different with previous examples. The mirror image we draw, and then the other possible stereoisomer, another one. Now you can see these two are mirror image, and they are enantiomers, no problem. These two looks like they are mirror image, but they are not enantiomers. They are identical. Why? If you rotate this isomer 180 degree, it will exactly same as this. That's superimposable. So superimposable with the mirror image, they are not chiral, and they are exactly the same. We call them meso compound. To be a meso compound, it must have more than one asymmetric centers, and they must have an internal plane symmetry. For this meso compound, the internal symmetry is here. So you see this half and the other half are mirror image. So they have internal plane or internal mirror image. Okay, now what about the relationship of this enantiomers with these meso compound? They are, oh sorry, meso compound is achiral. I just mentioned that. Okay, now relationship of these two are still diastereomers. Okay, and these two also diastereomers. So these two are the same. Okay, so for this case, although in theory you have two asymmetric centers, you could have to 4 stereoisomers, but actually only 3. Okay, because these two are exactly the same. Another example of the meso compound is this dibromide. If you have this dibromide, this two asymmetric center, and you can draw the other stereoisomer, and this one and this one. And these two, they are mirror image, they are enantiomers. And these two, again, they are mirror image, but if you rotate this stereoisomer, is exactly same as this one. So it's identical, and this is meso compound. Okay, and of course, you can find internal mirror here, internal plane symmetry. So that's why this is meso, and this has more than one asymmetric centers. Now, that's diastereomers, and that's also diastereomers. Now, let's summarize. This is the molecule with more than one asymmetric centers is chiral, but it can be meso. That will be achiral. So that's why we say unless it's meso. If the meso is achiral, but if it's not meso, a molecule with more than one asymmetric centers, asymmetric center usually is chiral. Okay, that's all I want to talk. If you have any questions, please let me know. Okay, good luck.